Okay. Yes. So in the previous class, we had stopped with three-dimensional transformations, and in that we were looking at the rotation of an object in three-dimensional form, right? So today let us see about the other conditions. So in the same rotation itself, in three-dimensional transformations, the other one is rotation about any line parallel to any axis. That is, the object may have at least one line which is parallel, or it may not be. Okay, right? So, but we have to rotate it with respect to one of the axis, either with respect to x-axis or y-axis or something like that. So then what do we do? How does it actually happen? Because once it is, since if any one of them is there, it is okay, we can find out the angle theta, right? And we can do the excuse me, the transformations or the rotations in this case. But if it is not that, the others the other lines will not be there, right? So then what does it do? How does it take place step by step? So what happens now? Let us have an object over here that has been shown. uh, the object that is shown over here. So this is the three axes x, y, and z that we have. So we have to first make at least one of them, at least this particular line, to be parallel to the x-axis. So what they do is we have to translate it. That means make it to the move it to a required position. So we have to change the coordinates of this so that it becomes horizontal or parallel to the required axis of rotation, right? So now it has become parallel, right? Now what is the need? Next is what we actually want is to perform the rotation. So now what will happen to the object? Okay, to the object, the rotation is going to be performed along the x-axis in this case. With reference to x-axis as the center, the rotation is going to be performed. So that is why here rotation with respect to x-axis for a given angle of theta has been mentioned, right? And after that, okay, so now once it has been rotated with respect to the x-axis, now we have to put it in the rotated form in this, in its original position, okay, in its original place, right? So what do we do is we made the translation, right? We had made the translation. That means this is the original position. For this position, we should have the rotated object, a rotated position. But what have we rotated for? We have rotated the object once when it is parallel to the x-axis. So once it is parallel to the x-axis, we get this rotated image. So, but this is not the original position where it should have been, because we have already translated. So after rotation, what we should do is we should do the inverse translation, cancellation of this values. So we have to do the last step is the inverse translation, so that the rotated image will go back in the rotated form itself, okay, in the same position how it was tilted, okay, and go back, and it is to be fit into the same original position itself. That is why we get this. Now once when we look this, it has been rotated, and now if we take a look at this, this is no more parallel to the x-axis, right? So this is what happens to the any line parallel to any axis. We have to do that sometimes, because we always cannot expect that the object will always have lines parallel to the axis. So there is another possibility problem, different case, not a problem, different case, where what happens? No line of the object will be parallel to the axis, to any of the axis. So if I have any, like just say for example, uh, like say for example, if I have any oval shape or a vessel kind of thing, so none of these things is parallel to any of this axis, neither this line nor this line nor this. It is not parallel to x, y, or z. Nowhere it is parallel. Now what do we do in that case, right? So if there is no line at all parallel to the any of the axis, then how do we rotate? But still we have to rotate. So this will generally have wherever we have curvatures, convex shapes, and all those things we have. So what will happen? So let us take that that initially it is the object is over here shown in the dotted line at a particular angle, right? At a particular angle. So what we will do is we first do the translation. We get this object to its origin. We shift it to the origin. That is what has been indicated. And here we get the, now we have not tilted anything. We are only translating. We are only moving the object to the origin so that our rotation becomes easier. Now we can easily find out what is the theta angle, what is the difference. Okay, how much is the difference with respect to the x axis or y axis or z axis. In this case, it is with respect to the z axis. Now what they will do is they'll perform the rotation with respect to z-axis. Let us assume we are going to perform the rotation with respect to z-axis. So this line, after performing with respect to z-axis, what is it going to do? We are going to make it with respect to the parallel to the z-axis so that it is going to become like this. So that is why this dotted line that is over here will now merge with the z-axis itself, and it continues on to whatever the length it is present. So now this theta has been rotated in with respect to z-axis for an angle of theta, right? And next is what? Now do the required rotation. Okay, now do the required rotation. It has to be rotated in the clockwise direction or anti-clockwise direction, or top to bottom or bottom to top. That can be easily performed because now we have at least one of them parallel to the any one of the axis. Now our rotation job becomes easier, right? So after performing this required rotation, what it will do? So now the image has been rotated with respect to this, right? Now what we do is, now we get it back. The next step is we get it back. That means once again in the rotated form, we get it to that same angle of theta that was present over here. Nothing but inverse translation only, we can say partially. We are only doing the inverse rotation. So we are getting it back to the, so that it is going to be joining to the origin, but at an angle of theta that was initially present. And then the last step is move it back to its original position. That is nothing but the inverse rotation. Move it back to the original position. So after rotation, that rotated object should be moved to its original position. So whatever was the distance from x, y, and z axis, put it back into that same place. So in this sequence of steps only, whenever we do the rotate command, the operations takes place in this particular sequence, depending upon whether the line is parallel or not, or at least one line is parallel, or whatever the lines that we choose from the object with respect to the axis. Or if there is nothing like this, we have only a curved object like this, like a pot, okay, then what do we do? So like this, these set of steps do take place in the background of the computer, right? So the next thing is about the scaling in three-dimensional form. So scaling in three-dimensional form. So once again, we have, say for example, we have our x, y, and z axis. So we have to scale it with respect to the origin. So what should be the size of magnification at its origin in three-dimensional form? So the new value should become x dash, y dash, z dash, but its initial point is x, y, and z. So scaling factor should be as usual. What should be the scaling factor with respect to x, scaling factor with respect to y, scaling factor with respect to z? That determines the x, sx, sy, and sz, right? So what happens over here is nothing but just like our two-dimensional scaling factor, x dash will be over here, okay, will be x, okay, into the sx value, the scaling factor, right? Where so as we have mentioned in the two-dimensional form, if sx, sy, and sz all are greater than 1, then the object is going to be magnified. It is going to become bigger in size. If the value of these sx, sy, and sz is less than 1, the object is going to be diminished. It is going to be zoomed out. Okay, right? So this was what is going to be done with respect to the origin, right? So the other case over here, with respect to scaling factor, we cannot always have the object at the origin itself. Now, what about if the object is not at the origin, right? But we still have to do the scaling. So what do we do in that particular case is that, so first thing is, let us assume that there's an object over here, okay, x-axis, y-axis, and z-axis. Okay, so this point has got x, y, z values. Okay, that is the initial point. Now, before we perform the scaling with respect to any point, where the point can be at xf, yf, and zf. That means it carries some values, but it's not at 0, 0, 0, right? It is somewhere over here. So then what do we do? First is to translate this to the origin. So get this point to the origin, shift it to the origin. So that is nothing but translation. So if this value is got, say for example, 2, 3, and 4, that is 2 values in x coordinate, 3 values in y, and 4 values in z. Okay, then to bring it back to the origin, so we have to do is -2, -3, and -4 is the values with respect to x, y, and z, so that if we minus this, then this point will move to the origin. That is why we are going to minus it with the same values, translate it, move the point to the origin. Then is the perform the scaling operation, just as mentioned previously. Perform the, now the point is at the origin, perform the scaling operation sx, xy, sy, and sz, right? Then after performing, put it back. After scaling, either it has been enlarged or it has been diminished, put that object back to its original place. So put it back to xf, yf, zf, that is 2, 3, and 4. So that is nothing but we are going to do the inverse translation operation. So the 3 steps that we are going to do is translate it to the origin, do the scaling, and then put it back to the original position, that is the inverse translation. So when we write all these things in matrix form, what does it happen? The resultant matrix for this will be, okay, 1, 0, 0 minus xf, because it is going to be for x dash value over here. It will be what? We have to first put it to the origin. So we have to get it back to the origin. So x dash should be first with minus xf value, right? So that is why xf value comes into picture. Similarly, yf and zf, and finally the unity matrix number, and that will be the translation matrix. And then, as usual, since it is in the now in the origin, the next one will be the multiplied by the scaling factor matrix. Okay, and then finally, the step is put it back to its original position. That is the inverse translation. So inverse translation, put it back to its original value. So in this case, 2, 3, and 4 is the value. So it should have 2, 3, and 4. So xf, yf, and zf are the initial values. So put it back to that itself. So multiplied by these these three matrices, along with the wherever the point is being there, along with its scaling numbers, the object is to be scaled and put it back to its original position. Right. So this is how the system solves these problems. Yeah. And yes, the next one, the last part that we have over here is about the reflection over here. So reflection in this case, okay. So just a second. So we would have seen something like this. Nothing but our x, y, and z coordinates. The 3 planes that we'll generally have once when you open any uh, solid modeling packages. So xy plane, yz plane, zx plane. Sorry, this is yz plane and this is the xz plane, right? So our 3 axes. So what we need over here in modeling is that we generally use the any of the plane to draw. Okay, and once we draw, say for example, I take this front view and we get this window like this. So now what I will do is I have the x and y axis, I will draw the object. So I will just make one, say for example, I'll just make one rectangle over here, which is only the sectional view. Now I have to rotate this, right? I have to make a mirror image of this. Okay, I want to have a mirror image of this. So once when I get back, once when I come out of this two-dimensional, I get back to the screen so that the object is like this placed over here. Now what do I want? It is at some distance from this plane. Okay, and it is just like this in the front view. I want the same copy to be over here onto the other side of the plane. I need it over here, right? I need it over here. So what should we do? We have to select which is the plane on which the object has to be reflected. This is the plane that we want to be reflected because this is the dividing portion between the left and right side, or the two portions where we have one side the original and the other side the mirrored image, right? So with that, so we can have one was over here is about xy plane, do the reflection with respect to xy plane. So if we remember in the two-dimensional form, if we have an object, or if we have an object over here, this is the x coordinate, y coordinate. I just want to have it over here. So in this case, what happens? The x value is going to be same. Okay, uh, at whatever is the distance should be the same. Okay, but the y value will change, right? So this is the x value at what distance it is. X value is not going to change. Y value will change because it will become negative y because it is in the fourth quadrant as of now, right? So similarly, when we do the reflection with respect to the z-axis, so if we have like this, so this is the z-axis. Now I want to do the mirroring option with respect to the z-axis. Okay, that is the object is over here. It is at some distance from x, y, and z. Okay, now I want to have this object to be put onto this side. So this becomes uh, negative x minus x value because this is x-axis, this is y-axis, and it is going to be onto the negative side. So I'll just redraw it once again. So if we have an object, so this is x-axis, y-axis, z-axis. Now I have the object somewhere over here. So this is at a distance of x and y and z. So it has got x, y, and z values. I want to mirror it. So this is the about the z axis. I want to mirror it. Now it is here within this plane. Okay, now I want to have this object here. So what happens? It is going to be at the same height. It is going to be at the same distance y plane, but this is going to be what? This x-axis onto this side of the plane, it is going to be minus x. Okay, but at the same distance because this is going to be the center. So if this is at a distance of 2 from uh, from the x-axis at a distance of 2 in that is the x coordinate, here it should be at a distance of minus 2. So here we have this. Okay, so this is what happens with respect to the z-axis. Okay, that is the xy plane. Okay, so xy plane, what happened is that, all right, so just a minute, sorry. Okay, this is with respect to xy plane, right? So xy plane, yes, this is our xy plane. So object is somewhere over here. Now, after this plane, this portion is the minus z-axis, minus s. So I want to have this object here, this side, after the plane, back side. So negative z-axis, whereas the xy is going to be at the same distance. So there is no change in those values except for the z-axis because it is going to be rotated with respect to the reflected with respect to the z-axis. So similarly, we can have it with respect to yz plane. Okay, we can have it with respect to yz plane. Okay, that is this plane. That means having the object over here, right? Okay, so in that case, if you look here, x-axis becomes negative, right? And similarly, we can have it with respect to XZ plane, that is this one, this plane. XZ plane is over here. So what is going to happen? This object should be moved below this plane. So Y axis over here is going to be minus Y. Okay, right? So thereby only for that particular thing we will have the, it's nothing but a unit matrix only, but only for that particular axis along which it has to be reflected, it will have a negative value of 1. Remaining all other things will have only one, only positive unit 1, right? So this is about the reflection. Yes, yes, this is we have to have this idea because some of these things is required for solving the problems also, right? So next we'll go to the other one, which is about, which is the, we'll see about what is this back face removal algorithm. So that thing, but first thing is that visualizing the three-dimensional objects on a 2D screen, visualizing this. So we'd have done this, especially in when you draw isometric drawing. Okay, we'd have drawn it, right, and we'd have given this also. Now this is actually how the object looks, say for example. Now when we do isometric drawing, whichever the faces or lines that is behind, okay, in isometric drawing, we'll draw it like this, so that only the faces that is there in front is going to be visible, but not which are the faces that is there backside. So these two faces are not going to be seen. Now how does the computer solve this, right? So thereby there needs to be an algorithm that has to be written where the computer detects which are the surfaces which is in front, which are the faces which is behind, and suitably it is going to remove the faces which is going to be hidden, or hidden surface or hidden lines. It is both of them for an object. So how does it solve? So thereby we need some algorithms. One is the backface algorithm that we need to know. So in this backface algorithm, what happens here? The face of the object is going to be visible if the normal vector in the direction of the outside of the object is pointed towards the viewer, is going to be pointed towards the viewer. So what they are trying to say over here is that, now say for example this is the object, okay, and what is going to happen now, just a second. Okay, in this case what is going to happen, the viewer is over here, the viewer is here. Okay, this is the object. So for every surface, totally we have over here 4 plus 2, 6 surfaces. So if you take up this surface, the object to, this is the surface that he is going to view. This is the viewing direction. So the normal to this is over here, which is going to be pointed outside. So there is no other surface on top of this or anything like that. So thereby what happens? The vector m into n value, if it is going to be greater than 0, it is going to be a visible surface. That is how it calculates, right? The outward normal vector n has to be positive component, right? It has to be a positive component. Okay. Now the next condition, what is going to happen? So what it is going to do? It is this algorithm is going to do for every surface from the viewer's end. What is the normal for that? Right? What is the normal or a perpendicular direction vector for that viewing direction? Okay, and it is going to see whether this is going to be positive or negative. And the multiplication of these both viewing vector and normal vector, and what is the value of this? That is the product of m into n, viewing vector into normal vector. If it is greater than 0 for every face of the object, it is, if it is going to be greater than 0, it is going to be visible. If it is going to be equal to 0, then it is going to be displayed as a line. It can indicate, now how does it identify that this is the end of the surface? Okay, and it has to draw a thick dark line. Okay, how does it draw a line is based upon this, right? So there ends this. So here it ends, right? So here it ends. So similarly this, even though this is one surface and this is another surface, the joining line is over here for these two surfaces, right? So it is going to be 0. The multiplication we obtained over here will be 0. So thereby it will be indicated as a line. But if this is going to be negative, okay, that is less than 0, then that particular phase itself is going to be invisible to the viewer. Okay, so this is how this algorithm actually works. There's a mathematical sequence and a format in which this algorithm is written. Okay, but anyway, the idea of this algorithm is by adding the multiplying these vectors, okay, the viewing vector and normal vector for every face of the object, and considering each one of them whether it is going to be visible or not. So based on that, the object is going to be projected either as a visible surface or as a hidden surface. Okay, so this is the basic algorithm. So this is going to act as a preprocessor for every other algorithm. So there is something called as visual display systems, in which all these algorithms are used. There are many different types of algorithms. The basic algorithm is this backface algorithm. This is the preprocessor. So the system can use any other algorithm also, but before it runs that algorithm, this backface algorithm is going to function first. Okay, so this is what is going to happen in this backface algorithm. The disadvantage of this backface algorithm is that now if we have an object like this, we cannot say it has no particular surface at all. Every surface is either concave or convex, right? There is no flat surface at all for this except this ground surface, the plane, the base. Nothing else is as a flat surface. This backface algorithm can detect only for flat surfaces. But if it is going to be concave or convex, it becomes very difficult for it to identify whether it is going to be hidden or whether it is going to be uh, the visible surface, because this algorithm is going to work only for a surface, only for a face. It should have a plane surface, not a convex or concave curvature shapes. No, it does not work out on that. So this is one disadvantage of this algorithm. The next disadvantage of this algorithm is that, say for example, if we go to the next one, a trapezium, hollow trapezium like this, if we take, okay, if we take up a hollow trapezium like this, okay, if we take a hollow trapezium like this, yes, and we are going to apply backface algorithm. Yes, now viewing from this end, yes, this face is visible, this face is going to be visible, this face is going to be partially visible, this face is going to be partially visible. Now what does this algorithm do is, so every time it is going to take place with respect to the entire face, but here it is going to be partial. Now it does not detect how far it is this face, how far it should be visible, how far it should not be invisible. It becomes very difficult for it to analyze. So backface algorithm cannot be used in these both cases. So there are cases like this where it cannot solve such problems. So this is always there for backface algorithm. But predominantly backface algorithm is always used first, and the remaining next step we will see this how to solve this further on. First it is going to run the backface algorithm always, right? Okay, yes, we'll stop here for today. Okay, so just go through this. Okay, right, today it's been time up.